Okay, now the next experiment I've got for you is slightly different. What we've got here requires a more variable power supply. So instead of using loads of different batteries, what I've got is a power supply here where I can vary the voltage and I've got an ammeter for measuring the current in series, and I've got a voltmeter for measuring the voltage in parallel. And I've got two components here. I've got a resistor, which we're not particularly interested in at this point. The resistance of the resistor is designed, as the name suggests, to stay fairly constant. But it's there to make sure that the current doesn't get too high for this component here, which is a light emitting diode, an LED, which you've seen lots of. But for today we're really only using it as a diode, because a diode is a very important electrical device. We use them in many different ways, and it's not typical of the electrical devices that we've studied, so we need to look at it in a little bit more detail. The first thing we need to know about a diode is that it has a preferred direction. If you look at the symbol for a diode, either a light emitting diode or a normal one, there is an arrowhead facing in one direction, and that is the direction that electricity will flow. Be careful, that direction of electricity will be for conventional current, so it'll be running from positive to negative, even though we know the electrons go the other way. So the diode only lets the electricity through one way. If I increase the voltage, we can put 1 volt, 1.5 volts, 2 volts, 3.5, 4, absolutely nothing happens. Nearly 5 volts, I don't want to take it too high because I will eventually break this device if I put too much voltage across it, but certainly no current will flow. In the other direction, however, diodes are designed to let the electricity flow. But only when the electricity gets to a certain level. So we've got no current at the moment and no voltage. If I increase the voltage to 0.8 volts, nothing. 1 volt, still nothing. And the LED isn't lighting up either. 1.5 volts, still nothing. But once we go beyond that, 1.6 volts, we now have both a light LED and a current. Not very large, because we've got that resistor in there as well, but still we do have a current. And as I increase the voltage a little bit further, the bulb gets a lot brighter and the current is increasing as well. If I take it much higher than that, the LED would break, and well, we don't particularly want to do that. Well, we don't normally. Now, we're back with our variable power supply, we're back with our ammeter, we're back with our voltmeter, but this time we're going to pay some more attention to that resistor. Remember, all it's done so far is try to protect that LED, and until we took it out of the circuit, the LED was safe. However, this resistor is designed to reduce the current that flows when a given voltage is put in, and it's a 100 ohm resistor which I've picked. Okay, the table of results is available separately, but all you would do is simply increase the voltage that flows through the circuit, so perhaps you might measure it every 1 volt, and you find that the current increases as the voltage increases. So at 1 volt we've got about 0.01 amps, at 2 volts we've got about 0.02, 0.03, at 3 volts 0.03, 0.04, and so on, all the way up to, let's take it up to 10 volts. Be careful when you get to these kind of voltages, because the resistor will be warm and we've got about 0.1 amps. In other words, the voltage and the current are proportional to each other and increase at the same rate, but the current is approximately 100 times smaller than the voltage. Now, with a resistor, unlike the LED, the direction of the current isn't important. So if I swap the positive for the negative and do the same experiment again, we start to get negative readings, but we find that at about 1 volt we have minus 0.00, but nearly minus 0.01 at 2 volts, nearly minus 0.02, and so on at 6 volts minus 0.06, and at 10 volts minus 0.1 amp. So the resistor is designed so that its resistance stays constant, its relationship between voltage and current remains constant, and that means you should get a straight line for your graph. Again, the graph is available separately and it's also in your textbook. If we look at one last component before we leave the idea of current and voltage behind, if we look at one last component, let's make it the bulb, the filament bulb, the old-fashioned bulbs that are being phased out. And the reason why they're being phased out, as I'm sure you're aware, is that they're not very efficient. Not very efficient at all. They're much better at generating heat than they are at generating light. That's how they generate their light. The metal becomes hot enough to glow. But as the metal becomes hot enough to glow, it also means that the electrons are finding it harder to get past all of the atoms that are now moving more because they've got more heat energy. And therefore, the resistance of the bulb won't stay the same. As more and more electricity goes through, as it gets hotter, the resistance will increase. So if we start off at 1 volt, minus 1 volt actually, because we're still about minus 0.6 amps. So if we were to double that, that's about 1.4 actually, so if we take it up to 2.8, it hasn't doubled. 0.2. We increase it even higher if we double that to about 6 volts. You see the bulb is getting brighter as we go up. We've now got 1.1 amps. Double that again all the way up to 12. But the current hasn't gone up as quickly. Now, a bulb is like a resistor in that it doesn't care which way round the electricity is flowing. So if I swap the leads over, at 12 volts, we now get positive values. As we bring them back down, they go down at about the same rate. And the current is not going up nearly as fast. Again, the results are available in both the table and the graph, and they clearly show that as the voltage increases, the current doesn't increase as fast. And that's because the resistance is increasing as the bulb gets hot, whether or not the electricity is flowing one way or the other.